Welcome everyone. We are discussing curve sketching today. So recall what was your vertical asymptote. So the vertical line, the line which is vertical, and vertical line is given by x equals to a. Such a line is a vertical asymptote if, so let's see this scenario. In this case, your x equals to a is a vertical asymptote. If your graph comes very close to it as you approach to a, but does not touch it. Okay, so the scenario could be either it could approach as x approaches to a, your f of x can go to plus infinity from both sides, or as x approaches to a from the left, your f of x can go to infinity, or as x approaches to a, your f of x can go to minus infinity, or as x approaches to a plus your f of x goes to plus infinity, or as x approaches to a plus your f of x goes to in minus infinity. So all these cases are the cases of uh, uh, give rise to a vertical asymptote at x equals to a. So we discussed this already when we were considering the limits. So let me recall. So in the case one, we have limit as x goes to a, f of x is infinity. In this case, we have limit as x goes to a, you're approaching from the left. So as x goes to a minus f of x is infinity. In this case, you have limit as x goes to a plus f of x, because you're approaching to a from the right, is infinity. And similarly, in this case, you have limit as x goes to a, f of x is minus infinity, and so on. So whenever your function has the following property, any one of these limits being plus or minus infinity, then you say that x equals to a has a is the vertical asymptote for your function. Okay, so note that graph can have any number of vertical asymptotes from none to infinitely many. Say, for example, if you want a graph with 3 vertical asymptotes, so let's take x minus 1, for example, x minus 2, x minus 3. Yeah, so this graph will have vertical asymptotes at x equals to 1. So the line x equals to 1 will be the vertical asymptote. Line x equals to 2 and line x equals to 3 also is a vertical asymptote. So you can have as many vertical asymptotes as you want. Okay. Now again, recall what was the horizontal asymptote. So it's a horizontal line. So note that y equals to L represents a horizontal line, right? So horizontal line, y equals to L is a horizontal asymptote of f of x if either of the following is true. So recall, so it can come closer to a horizontal line only when you're going to either if x goes to infinity, your f of x gets closer and closer to this value L, right? So, so the definition is the line y equals to L is the horizontal asymptote for f of x if either limit at x goes to infinity of f of x is L, or limit at x goes to minus infinity of f of x is L. Okay, so if you look at this case here, this example, you can see that as x goes to infinity, your f of x is getting closer and closer to this value, whatever this is. Let's call this as L. And as x goes to minus infinity, your f of x is going closer and closer to this value. Let's call this as M. So there are two horizontal asymptotes in this case, y equals to L and y equals to M. These lines are the these horizontal lines, these are horizontal asymptotes. So note that there can be at most two horizontal asymptotes, right? I mean, in this case, in this graph here, you can see there are two horizontal asymptotes, but function can have no horizontal asymptotes, one horizontal asymptote, or at most two horizontal asymptotes. Okay, so these are the possibilities for horizontal asymptotes. Yeah. Now there is another kind of asymptote which is called slant asymptote. So if you can have vertical line as a vertical asymptote, horizontal line as a horizontal asymptote, and if you take any other line except for vertical or horizontal, and if your graph comes very close to it, as you can observe here, as x goes to infinity, your graph is getting closer and closer to this line here, right? Similarly, if x goes to minus infinity, your function is getting closer to this line again. So getting closer to any other line, which is not vertical or horizontal, gives rise to the slant asymptote. So a line is given by equation y equals to mx plus b. So line y equals to mx plus b is a slant asymptote for f of x. If what happens if your graph gets very close to the line, right? That means what? That means the y value of your function, as you go further and further, the y value, so here the y values were far apart. But as you go closer and closer, the y values become very close to each other, right? So this means the y value for your function, which is given by y equals to f of x, so f of x minus y value for your line, which is y equals to mx plus b, so mx plus b, this should be 0, right? This means that they become very close as x goes to infinity. Similarly, that can happen in the other direction as well. So x goes to minus infinity of f of x minus mx plus b equals to 0. So if either of this happens, so or, so if either of this happens, you get a slant asymptote. So again, since there are two directions to take, as x goes to infinity or x goes to minus infinity, your graph can have at most two slant asymptote. Here I should add at most two horizontal asymptotes. All right. So at most two slant asymptotes and at most two horizontal asymptotes. Okay, so let's try to do a problem and understand this in more detail. So find the vertical line, which is the asymptote for f of x equals to 2x upon x minus 4, or find the vertical asymptote for this function. So notice the following. What we need is limit as x goes to what? X goes to a, f of x is plus or minus infinity, or limit as x goes to a plus f of x is either plus infinity or minus infinity, so plus or minus infinity, or limit as x goes to a minus f of x equals to plus or minus infinity. So we need this for line x equals to a to be vertical asymptote. Okay. So now note the following here. So if you look at 4, it's not defined, right? Now if you approach to 4 from right, so we are approaching to 4 from right. What is happening to your function? So if you approach to 4 from right, x minus 4 is going to be positive, right? Because x is here. So x minus 4 is going to be a small positive number. Since 2x approaches to 8, which is also positive, we'll have 2x divided by x minus 4 is a very large positive number, right? Because your top is stabilized at roughly 8, but the denominator is getting smaller and smaller as you're approaching to 4. And if you're approaching to 4 from right, it is a very small positive number. So the whole thing becomes infinity. So we get that x equals to 4 is a vertical asymptote. Right. So this is how you would find the vertical asymptote. So let's look at the next problem now. Finding the horizontal asymptote for f of x equals to absolute value of x over x. Now in this case, if you try to draw the graph of this function, you will notice that at 0 it is not defined. However, when this is greater than 0, absolute value of x becomes x, which is 1, and absolute value of what? When x is less than 0, you will have absolute value of x is minus x, so minus x over minus x over x, which is 1, minus 1, my bad. So when you draw this, the graph actually looks like this. Right? Okay, so this is how the graph looks like. There's a hole, it's constant. Now we want to compute the horizontal asymptote. So we must compute the two limits as x goes to infinity and x goes to minus infinity. So let's look at that. As x goes to infinity, that means x is greater than 0. So absolute value of x is going to be x. So therefore, limit as x goes to infinity of absolute value of x over x becomes limit as x goes to infinity of absolute value of x is x, because x is positive, and that when you cancel out, you get 1. Similarly, as x goes to minus infinity, x is less than 0, we get absolute value of x equals to minus x. Therefore, this limit is going to be limit as x goes to minus infinity of minus x over x, which is minus 1. So therefore, this graph has how many? Two horizontal asymptotes, namely y equals to 1 and y equals to negative 1. Now, so you see that this dotted lines are the horizontal asymptotes. Now note that this dispels dispels the idea that that the graph cannot touch the horizontal asymptote, right? You see the graph and the horizontal asymptotes are identical in this part and identical in the part here. So yeah, so graph can basically cut or touch the horizontal asymptote infinitely many times. Yeah, another interesting example which you should look at is limit as x goes to infinity of sine x over x. So if you look at this function, you will see that this guy is limit as x goes to infinity of this is 0 using the squeeze theorem, but you will see that at x equals to 0, it's not defined, but it's roughly 1. So this will basically take too many. It will cut the graph too many times, right? Infinitely many times. So so this is a misconception that a line cannot, a graph cannot cut your horizontal asymptotes infinitely many times, right? Okay, right. Now, next step is about how to find the slant asymptotes. So let's say f of x is a function given here, and you want to basically find out the slant asymptote. So first of all, will the slant asymptote exist in this case? Generally, the slant asymptotes exist if the degree of numerator is degree of denominator plus 1. Okay, so we'll perform the long division here, minus 3x squared plus 4 divided by x minus 1. So let's perform this. So you can either use synthetic division or long division. So I'll show you a long division here. So 3x plus 4 divided by x minus 1. So how many times x goes in minus 3x squared? Minus 3x times. So minus 3x squared plus 3x. Now we need to subtract these guys. So when you subtract, you get minus, this will go away. You'll have minus 3x plus 4 and then minus 3 times. So minus 3x minus of minus of plus 3. When you subtract, you get what? You get 1. So when you divide this, you will see that it's going to be minus 3x minus 3 plus 1 upon x minus 1. Now think about it. When you look at this expression here, as x becomes really large, 1 upon x minus 1 will go to 0. So that means your graph will get very close to minus 3x plus 3. So that's the idea. So let's try to look at that. So if you put minus 3x minus 3 here, you will get 1 upon x minus 1. Limit, I should write it as limit. So limit as x goes to infinity of minus 3x minus 3. Sorry, my bad. 1 upon x minus 1, and that is going to be what? 0, right? So similarly, because as x goes to infinity, 1 upon x minus 1 goes to 0, right? Because if x goes to infinity, the denominator is still getting bigger and bigger, and 1 over that becomes smaller and smaller and becomes 0. The same way, if x goes to minus infinity of this guy, 3x minus 3 is again limit as x goes to minus infinity of 1 upon x minus 1, and that is also 0. So in this case, we get what? Y equals to minus 3x minus 3 is a slant asymptote of f of x. Okay, so this is how you get to the slant asymptote. Make sense? All right. So let's move ahead. So this is how you basically consider the asymptotes. Now there are a few more points to consider when we are sketching the graph of the function. So other considerations are the endpoints or the special points of the domain. So note the following: if the domain of the function does not extends out to plus or minus infinity, we should ask for how does the function, or ask about what happens to f of x or your function as x approaches to the boundary to the boundary of domain. An example here would be, so let's consider the following. Let's take y equals to f of x, which is 1 upon r square minus x squared. Now, here, if you look at this example, the y becomes, as you approach to r or plus or minus r, y basically becomes what? Becomes infinite, right? Or rather, it's a proper way to say is that y approaches to infinity as x approaches to plus or minus r. Now, we may also identify that this behavior, because at x equals to plus or minus r, the denominator of the function is 0. Therefore, it blows up to plus or minus infinity, right? Now, there are a few more points to consider where the derivative fails to exist. It could be either a cusp, like you have in the case of x to the power 2 by 3. Recall the graph looks like this. So there's a cusp, the derivative does not exist. Or basically, we have corner, like absolute value of x, right? So where the function has a cusp or a corner, and we should take special care of the function at that point, right? Function does at such a point, right? What kind of behavior it has at those points. So another consideration is the functional symmetry. So So note that, recall, f of x equals to x squared. This is an even function, so such functions are symmetric around origin, sorry, around y-axis, right? And consider f of x equals to x cubed. So this is an odd function. So odd functions are symmetric around origin. So symmetric around y-axis. That means if you reflect in the y-axis, you get the same thing. And here in this case, this is symmetric with respect to x-axis. Sorry, with respect to origin, my bad. Okay, so this is how the function odd and even works out. So, so function symmetry will help us. It helps us in sketching its graph. So even function means f of what? F of minus x equals to f of x, and it helps us basically. So its graph is symmetric with respect to y-axis. So whenever x to the power n is an even number, we get a even function, or cosine is an even function, or sine to the power any even number is also an even function. Similarly, we have odd functions. So in odd function, we have f of minus x equals to minus f of x. So the graph is symmetric with respect to origin. And you can see that x to the n, when n is odd number, will satisfy this. And so does sine. You can look at the sine or tan graph, right? So for example, this function here is symmetric in it's a symmetric in y-axis, and hence it's an even function. You can see that this function is symmetric about origin, and it's an odd function. This is a graph of tan x. All right, so now most of the functions are neither even or nor odd, right? And they in particular do not have any particular symmetry. So but however, if we have a symmetry, we should exploit it. Okay. So now let's attempt to sketch a graph of a function. So suppose you're given this function, f of x equals to x squared upon square root of x plus 1, with f prime x equals to this and f double prime x equals to this. Okay. So now, first step, we'll find the domain of this function. So note that top is fine, but the restriction in the bottom for the domain, your x plus 1 has to be greater than equal to 0. And x is not equal to minus 1, because otherwise the denominator will become 0. So the domain is minus 1 to infinity, right? Because this both leads to x plus 1 being greater than 0, which is same as saying x is greater than minus 1. Now let's look at as x goes to infinity of this, x squared upon square root of x plus 1, and that you can check that this is going to be infinity, so there is no horizontal asymptote. Now the denominator is becoming 0 at minus 1. So let's investigate if it has a vertical asymptote at x equals to minus 1. So we'll choose to go from either side. So let's go x goes to minus 1 plus. We get, as x goes to minus 1 plus, you will see that the top will be fixed at 1, but the denominator is getting smaller and smaller with a positive sign. So this is going to be plus infinity. Right? So therefore, x equals to minus 1 is a vertical asymptote. Now note that you can't take x goes to minus 1 minus, because the function is not defined, right? On the other side, because function is not defined on the left of minus 1. Okay. Now to find the critical point, you have to basically consider two cases. F prime x equals to 0. In that case, the top is 0. We get x equals to 0 or x equals to minus. F prime x equals to 0 part of this one. Also, f prime x does not exist when x plus 1 equals to 0, but minus 1 does not belongs to domain of f, so not a critical number, right? So the only critical number is 0. So 0 is the only critical number. 0 is only critical number. Now we'll draw the sign chart of your f prime x. So in this case, what we'll do is we'll mark the points. So let's mark the boundary minus 1. 0 is your critical number. So take a point of your choice, say minus 0.5. If we take minus 0.5, right? So you also have to check. So when you're drawing the sign chart, you have to include the points, not only just the critical numbers, but also the points where the function is undefined, all right? So now that we have sign diagram, we can check that using first derivative test, f of 0, which is substituting 0 here is 0, is what? Relative minimum. And f double prime is greater than 0, right? Because this is always greater than 0 for all x belonging to domain f. So therefore f is concave up on all of the domain, and therefore there is no inflection points. And next lecture we'll study the interesting cases where there are inflection points and so on and so forth. So now let's draw the graph now. So first things first, at x equals to -1, we have a vertical. X equals to -1, we have a vertical asymptote. Now from 0 to -1, the function is what? The function is decreasing. Near -1, look at the sign. As x goes to -1 plus, the limit is infinity. That means the vertical asymptote. So because of that, the graph will be of the following form. Until 0, it is decreasing until 0, right? And the shape is concave up. So when I plug in all these three things, this is what I get. Now after 0, we have to see the function is still, so after 0, since the sign diagrams gives a positive sign, that means the function is increasing, yeah, and what sign does it has? It has basically a positive sign. So, and it's concave up because of f double prime being greater than 0. So this is how the function is more or less going to look like. All right. Sorry, we don't have to mark 1 here. All right, because 1 is not any of the special numbers. So it's all positive here. That's all. Okay. So this is the whole uh, curve sketching. Okay, so next class we'll discuss about how to do the other cases.